L02, two powerful theorems. The first one is parallel access theorem. Say we have some kind of a continuous distribution of matter, and say that we have a center of mass, say it's there, and then we have an axis here where it's going to rotate about this axis. Let's go ahead and give some parameters. There's the distance from the center of mass to the point where the axis goes through. We'll call this A, we'll call this B. And we're interested in this axis, so the R to some little piece of mass here. Let's call this a MI, a little piece of mass. That's the distance RI away from the axis. And let's look at the distance to this point relative to the center of mass has some xi. You can think of this as y and x. Now maybe you're a little bit careful here because this is a three-dimensional drawing. So really the y and x are in the plane, and then it's rotating about the z-axis. All right, so there's some kind of like z-axis here. And then we have x and y. So here, this would be yi, and this would be xi. So now to use the formula for the moment of inertia, we want the sum mi times ri squared. You want all these. But the ri squared here is going to be, from here, it's going to be the big x minus the a. So this is x minus a. See, xi is all the way here. And you basically want here, this, the red. So this part here is xi minus a gets you this. Right in here, see that distance there, xi minus a. And then similarly up here, this is yi minus b. So the moment of inertia, we're going to sum these. It's going to be mi times, and you put all this stuff in. And when we put this stuff in here, let's go ahead and square it. xi squared minus 2 xi a, and this is going to be plus a squared. And then plus, we're going to have this one, yi squared minus 2yib plus b squared. So what we did there is we put this in here, and this m is there. And then we then go ahead and squared it out. So what do we have? We have here mi hits the xi squared Then we have minus 2. A is a constant. We can pull that out. And this is going to be mi, that's this piece, xi. Then we have a squared times the sum of the mi's. And then we have, similarly with the y, so we have a mi yi squared minus 2b mi yi, and then plus b squared mi. Now notice that the sum of the masses is simply total mass, which we'll call big M. So this is going to be total mass, big M. Now notice that when you take mi xi and you are measuring with respect to the center of mass, that this is going to be 0 and this is going to be 0. Because if you're at the center of mass, the balance point, then when you calculate, see, the center of mass is, by definition, the mi xi's divided by the total mass. That's your definition of center of mass. But if the center of mass is our origin, in other words, when x is 0, y is 0, that's where we are, then the center of mass is 0, because that's our origin. And then similarly, y center of mass, which is mi yi over m, that's going to be 0 also. So therefore, the numerators are 0, which is what you have here. So then you get, for the moment of inertia, you have the sum mi xi squared. You have this first piece, this survives. And we're going to have this part here plus big M times a squared. And then we're going to have mi yi squared, that's this part, plus m b squared. Then we can write this as the sum of mi xi squared plus yi squared. We're combining these two. And then we have m, we combine the we combine this one with the last term. And that's going to be a squared plus b squared. Now, a squared plus b squared, if you have here, remember that a is here, and then if you have a squared plus b squared, Pythagorean theorem, that's going to be the distance your axis is from the center of mass. That's going to, well, it's squared, d squared. So this is d squared. And this is the moment of inertia measured from the center of mass. So that's the center of mass, moment of inertia. So we have this really cool formula that the moment of inertia about any axis is the moment of inertia about the center of mass plus the mass of the entire unit times the distance you are from the center of mass, where your axis is from the center of mass. So that's the parallel axis theorem. And that'll help us do lots of problems without a lot of calculus steps. The second theorem is the perpendicular axis theorem. Now for this theorem, actually it's easier. Say we have some kind of continuous solid. We want to go about this axis here. Let's call that the z-axis. And now I'm going to be very careful with my coordinate system. I like to always have a right-handed coordinate system, and that means we need to put x this way and y this way, the y-axis this way, and the z-axis up here. Because if you then use the right-hand rule with, or turning like with the screwdriver, turning x, if we're tightening from underneath, we want to turn x into y, or you can do it with like this, x into y. The z points up. That's the right-handed coordinate system. So that's always good to do. All right, so here, if we look at, say, some little delta m here, which is going to be mi, we'll just say mi, discrete, then this is going to have an x and a y. So this is going to be here, xi going here, and then this is going to be, that's the same thing. That's xi on either side, xi, and then yi would be, you know, we're looking at here a rectangle. So the x is along the x-axis, and there's this same value over here on the other side of the rectangle. And then y goes along the y-axis, but on the other side, the same thing. So here, we are at a distance, see, ri, from the axis. So when we write our formula down, going along the z-axis, you're going to have here the sum mi ri squared, since ri is measured in the plane of the unit or structure, and we're going to go around the z-axis. So now we're going to write this down where we substitute in for the ri squared using the Pythagorean theorem. That ri squared is the xi squared plus the yi squared. That gives us two sums, mi xi squared plus mi yi squared. But what is mi xi squared? Well, if you look at mi xi, that's xi is the distance from the y-axis. So these are distances from the y-axis. So this is going to get you the moment of inertia about the y-axis if you were going around this way, that way. Then what about the yi? Well, if you go yi, that's the distance from the x-axis. So that's going to be ix. If you were going around like this is the mass from the x-axis. So this is wild. This is saying that the z, moment of inertia, is equal to, we'll put this one here first, the x and the y, the sum. This is sum. Very, very impressive theorem. So if I want the moment of inertia about the z-axis, I add the moment of inertia about the x-axis and add that to the moment of inertia about the y-axis. These two theorems are the two powerful theorems that we will be using.